Which of the triangles, triangle DEF, triangle GHI, and triangle JKL, are similar to triangle ABC? And we have this triangle ABC. They've given us, or they've just marked one of the angles, and then they've given the lengths of the two sides on either side of that angle. And you might remember from geometry class, you can prove that two triangles are similar is if you can show, well, they have corresponding congruent angles. So let's say we're trying to compare this triangle to this triangle, triangle JKL to triangle ABC. So if you can show that they have two corresponding angles that are congruent to each other, and that the sides on either side, the ratio between the sides on either side of that angle are the same, then you're going to be dealing with a similar triangle. So for example, if we say that this angle corresponds to this angle, and they've already marked it to say that they're congruent, so that's a pretty good starting point. And if we could show that the ratio between this side and this side, side KL, is the same as the ratio between BA and KJ, then we can say that these two are similar triangles. Now you might be thinking, well, how did I decide to compare BC to KL and BA to KJ? Well, both of these are the two sides that essentially make up this angle, and BC is the shorter of the two. These are the two sides that make up this angle. Both of these are I guess you could say they're segments of the rays. They're parts of the rays that make up this angle. If you were to kind of continue forever, and the blue one is the shorter one. So that's the best candidate for KL is the best candidate to correspond to BC. Well, in order to do this, we're going to have to figure out the lengths of these sides. We're going to have to do it for all of these triangles right over here. And they don't give us the lengths, but this thing is sitting on a coordinate plane. Now, you could use the distance formula, but I like to just cut the chase. The distance formula is based on the Pythagorean theorem, and they've drawn a grid right over here for us. So we could just set up some right triangles to figure out. We can make each of these sides essentially the hypotenuse of right triangles. So to figure out the length of KJ, we could set up this right triangle right over here. This height is 3. This length right over here, we could count it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 units wide. If we wanted to, if we couldn't count like that, we could say, look, we're going from x equals -6 to x equals 3. 3 minus -6 is equal to 9. Let me make that clear. And that's essentially where the distance formula comes from. 3 minus -6. You're finding your change in x, and you're going to square it, and then you have your change in y, you're going to square it, and that's going to be equal to this hypotenuse squared. So let's think about, so this is going to be equal to the square root. I'm just using the Pythagorean theorem here. So I'll just call it, so let me just write it out so you don't think I'm doing some type of voodoo. So 3 squared plus, let me do a little higher because I have a feeling I'm going to use a lot of real estate. 3 squared plus 9 squared is equal to the length of KJ, squared. 3 squared is 27. Sorry, not 27. 3 squared is 9. 9 squared is 81. And then that's going to be equal to the length of KJ squared. Or we get KJ squared is equal to 90, which is the same thing as 9 times 10. And so KJ is going to be, it's the square root of this. So the square root of that is going to be square root of 9 times 10 is equal to the square root of 9 times the square root of 10, which is equal to 3 square roots of 10. So it's actually the exact same length as BA. Now let's do the same thing for KL. For KL, we could set up another right triangle right over here. So its height is 3, and its width is 3. This is 3 and 3 right over here. So we could write 3 squared plus 3 squared is equal to the length of KL squared. This right over here is 18 is equal to KL squared. And if you take the square root of both sides, 18 is, of course, 9 times 2. So this right over here, this would square root of 8. This is the square root of 18 is equal to KL. Square root of 18 is the same thing as square root of 9 times 2. That's just 3 square roots of 2. This is equal to 3 square roots of 2. So this is 3 square roots of 2. This is 3 square roots of 10. This angle is congruent. This angle is congruent to this angle right over here. So not only are ABC and JKL, not only are they similar, but these are actually congruent triangles. These are congruent triangles right over here, but they're definitely, all congruent triangles are going to be similar. So this one is definitely similar. JKL is similar to ABC. Now let's figure out all of these lengths up here. Well, you have, let's see, this is 1 and 1. So you could say 1 squared plus 1 squared is equal to EF squared, is equal to the length of segment EF squared. Or you could say EF is equal to, let's see, this is 2, so this is going to be the square root of 2. So actually, I should have done that in that blue color, because this will be the shorter. We want this to be the shorter side if we're comparing the two sides on either side of that angle. And now let's look at ED. So once again, we can set up a right triangle that is 1 wide and 3 tall. And so we could say 1 squared plus 3 squared is equal to the length of ED squared. See, 1 squared plus 3 squared, this is going to be 10. So we get ED is equal to the square root of 10. Now, is the ratio between BC and EF the same as the ratio between BA and ED? So let's write this down. So square root of 3, or 3 square roots of 2 over square root of 2 is equal to 3. So the ratio between these two blue sides, between BC and EF, is 3. The ratio between these two orange sides is 3 square roots of 10 over square root of 10. 3 square roots of 10 over square root of 10, which is also 3. So the ratio between these two corresponding sides are the same. The angle in between is congruent. So these two triangles are also similar. So EFD, or DEF, is also similar to ABC. So we have one more to think about. So HI is a candidate to be corresponding to BC. What's its length? Well, let's see. This is a right triangle that's width 2, height 2. So we could write 2 squared plus 2 squared is equal to the length of HI squared. This is 4, this is 4. So 8 is equal to the length of HI squared. And then we can take the square root of both sides. So the square root of 8 is equal to the length of HI, or we could say the length of hi, or the length of HI, is equal to, let's see, this is 4 times 2. So square root of 4 times square root of 2 is 2 square roots of 2. So this is 2 square roots of 2. And then the candidate to be corresponding to AB is HG. It's the longer of the two sides on either side of this angle. So HG, we can set up a right triangle. HG, we could set up a right triangle that looks like this. It's 2 wide and 1, 2, 3, 4, 5, 6 high. So we can write, let me scroll over to the right a little bit. We can write that 2 squared plus 6 squared is equal to the length of HG squared. So this is 4 plus 36 is equal to the length of HG squared. Or we get that HG is equal to the square root of 40. Square root of 40, let's see, how can we simplify that? That's the same thing as the square root of 4 times 10, which is 2 times the square root of 10. So HG is equal to 2 times the square root of 10. Now let's compare the ratios. The ratio between BC and HI is going to be 3 square roots of 2, 3 square roots of 2 over 2 square roots of 2, over 2 square roots of 2, which is 3 halves. And the ratio between BA, which is 3, let me do that in that orange color, which is 3 square roots of 10, 3 square roots of 10, and HG, which is 2 square roots of 10, is also 3/2. So all of these triangles are, not only are they similar to ABC, but they're actually all similar to each other.